Hello all, good evening. Can you hear me?
Yes, ma'am.
Yes, ma'am.
Okay. All right. So today is week 11 session. Um,
Good evening, ma'am.
good evening all. Yeah.
Ma'am, there is no session of week 11 open session.
What?
There is any,
Today is? Hello?
yes, ma'am.
Yes, ma'am.
Can you repeat? I couldn't hear it properly.
Week 11, in week 11 open session are not held.
Week 11. So the last session I had taken, it was supposed to be week 11, but you told week 10 is not done. So I started doing week 10. So we'll focus mainly on week 11, as tomorrow is the deadline also. So whatever doubts you have, let me share my screen. I will write it there and then we'll take it from the sequence.
Ma'am, actually week 11 summary has not done. Like there was no session for week 11 summary open session.
Summary session. Okay, we'll do a summary session. Okay, fine.
Ma'am, there was no open session for week 11.
Last
ma'am,
session, Friday session was supposed to be for week 11.
yes, ma'am, but ma'am had some miscommunication and she thought that there is week 12 session. So she had taken week 12
I'm talking
open
about
session.
the Friday session.
Yes, ma'am, Friday session. So she told us that the next session will be of the like in the next session she will take the open session for the week 11.
No, I'm talking about the Friday session. That happened on Sunday. Friday, I had taken the session. It was supposed to be for week 11, but you people told it is for week 10, so I started doing week 10. Okay, let's start then. Let me share my screen. Week 11. Can you see the screen?
Yes, ma'am.
Yes, ma'am.
Okay. All right. We'll do the summary also, but first, can you tell me the doubts that you have? Because tomorrow is your not solve with us. Tomorrow is your deadline for week 11, right? So I will take both of them together. So I will write it down, whatever doubts you have. Can you tell me one by one?
Yes, ma'am. I have an activity 11.3, last question number 5th.
Activity 11.3,
Question number 5th.
question number 5. Okay. Anyone else?
Yes, ma'am. I'm in activity 11.2, question number 2nd and 3rd.
Question number 2nd, 3rd. Okay.
Yes, ma'am.
You all would have watched the lecture by now, right? Because it has been released quite earlier. You all have watched the lecture? No, yes.
Have done.
Okay. Can you tell me the doubts you have any?
Yes, ma'am.
Oh, your voice is breaking if you're speaking. I'm not able to hear it.
Ma'am, can I ask my doubt?
But you can ask what?
Doubt. I have doubt in some questions.
Yeah, that's what I'm asking. You can tell me, I will write it here and then I will take this.
Sir, my doubt, ma'am, is my doubt is from week, sorry, activity 11.5, question number 3.
AQ 11.5, question number 3. Okay.
And 5 and 6.
5 and 6. Same activity.
Yes, ma'am.
Question number 5, question number 6. Okay. Anything else?
11.6, question number, let me check. Question number 5.
Okay.
Done.
In 11.58, question number 8 also. That's all.
Question number 8 also. Okay.
Question number 7 also, ma'am.
Question number 7 also. Okay. Anything else? Okay. We'll do these for now. If you have any other problem, you can let me know later. Okay.
Okay, ma'am.
So I'm assuming all of you have watched the lectures.
Yes, ma'am.
Yes, ma'am.
Okay. Did you face any problem in the lecture?
No, ma'am.
No. Okay. So we can skip the summary if you have no issues, and we can focus mostly on the problems.
Okay, ma'am.
Okay.
Ma'am, can you please give summary also at the last after the
Ma'am.
questions?
Ma'am, I
Okay.
have
So
doubt in
Hmm.
ma'am, I have doubt in hypergeometry.
You have doubt in
Hypergeometry and binomial. How to
hypergeometric and binomial.
yes, ma'am. How to distinguish the
Also in Poison, ma'am.
Poison also. Okay.
And binomial distribution also.
All the distributions. All the distributions.
Yes,
Okay,
ma'am.
let me do one thing. Let me start from the distributions. I will cover all the distribution, like what it is and what does the expectation and the variance looks like, what is the PMF looks like, okay, and what do they model. So I will go I will give a brief summary of all the things, and then we can move to the problems. If that is all right.
Yes, ma'am.
Okay. All right. Okay. Is it possible to share two screens? Yes.
Yes, ma'am.
Can you tell me how to do it? Mm. Okay, can you tell me what are you saying?
And you can use the button of right corner close and maximize between. You can use two screen at a time.
No, right now what are you saying on the screen? I'm sharing my screen. Can you tell me what can you see?
Ma'am, shared with me slides.
Okay. Yeah. So I will go through all the slides that are available to you, and I will just give a brief summary of whatever is there. I think there's some internet issue. Just give me a minute. Okay. So we have started from a Bernoulli distribution, right? So we are going to look at only the discrete distributions. All right. Continuous you would have seen in week 12. So in discrete distributions, you must have looked at the first, which is a very basic one, which is a Bernoulli distribution. Second is binomial distribution. Binomial distribution. Third is Poisson. Fourth is geometric. Fifth is negative binomial. And sixth is hypergeometric. Okay. Let's start from the Bernoulli distribution. So what does the Bernoulli distribution looks like? Like, let's say you have a random variable x, or and we are saying that this random variable is Bernoulli distributed with the parameter p. So whenever you have a situation like a yes or a no, a success or a failure, right? So such kind of situations are modeled using the Bernoulli distribution, where p denotes the probability of success. All right. Now, for example, and we are interested in okay. So when you toss a coin, suppose we are interested in the event if head has occurred. Right? So, you know, when you toss a coin one time, either you can have a head or you can have a tail, right? Now, if I just want to check, like I want to check whether a head has occurred or not, then you have only two possibilities. Either head has occurred or head has not occurred, right? HC. So my success is like I am interested in the event that head has occurred. So this event, I can take it as this is my success. This is what I'm going to define as a success. Okay. And if head has not occurred, this we are going to define as a failure. Okay. And probability of success, let's write the success as S. So probability of success, so let's note S as success as S, as small p. And this small p is what we are writing over here. Okay. So what we're saying, probability of success is p, and probability of failure, which we are denoting it as F, is 1 minus p. Why is that? Because since this is a Bernoulli distribution, you can have only two outcomes, either a success. So in case of Bernoulli, you can have only two outcomes, either a success or a failure. Okay. And we are saying success with probability p, small p, and failure with probability 1 minus p. Since you have only two outcomes and you know the probability should add up to 1. So if probability of success is p, then probability of failure should be 1 minus p. Okay. So this is what a Bernoulli distribution looks like. All right. Now, for example, here I had given you the example that toss a coin once and check whether the head has occurred or not occurred. Now, can I say like can we define a Bernoulli distribution when we are tossing a coin 2 times? Is it possible? Can someone tell me? Is it possible to define a Bernoulli distribution when the random experiment is tossing a coin twice?
Yes, possible.
Okay. So can you give me one example?
Like, for example, when I toss twice and probability of having heads twice
Okay.
is the success, let's say. Then remaining probabilities will be failures.
Correct, right? So that is also possible, right? So we can say, let's define my success as getting 2 heads. So if that happens, we are calling it a success, and others will be failure, right? So when you're tossing a coin 2 times, you will have the outcomes as head, tail, tail, head, tail, right? So, and you know the probabilities for each of these outcomes is just 1 by, for everything it is 1 by 4, 1 by 4, 1 by 4, 1 by 4. So what is probability of success here? It is just 1 by 4, which we can write it as P. And failure would be, probability of failure would be 1 minus 1 by 4, which is 3 by 4. Right? And you can add, you know that in the failure, you will, in the events, you will have HT, TH, and TT, and their probabilities will add up to 3 by 4. So probability of failure is 3/4. Okay, so this is how your Bernoulli distribution looks like. Now we'll move to a binomial distribution.
Ma'am, how does the Bernoulli distribution graph look like?
Bernoulli distribution graph.
Yeah.
You're talking about the PMF?
Uh,
PMF only, right?
yeah.
So X will take the value. You have X, you have fx of X, right? So X is taking the value 0 and 1, only two outcomes, right? So 0 with probability 1 minus p. So this is, let's say, 1 minus p. And one with probability p. Let's say this is my p. So this is my p. And this is my 1 minus p.
Ma'am,
Hmm.
so when X is 0, that means probability of succeeding, let's say that event is 0, failure is 1 minus p, which is y. Is that how you're?
Can you repeat? Can you repeat?
No, okay. So no, actually, see, on x-axis you represented 1 minus p. What is that 1 minus p? How did you get it?
Fx of X, no? On X, like if let's say X is Bernoulli p, so X is taking the value basically 0, 1. So 0, I'm saying it's a failure, and 1, I'm saying it's a success. Okay. So probability of 0 is 1 minus p. Probability of 1 is p. Right?
Yeah, can we take head and tail, ma'am, so that we can visualize what we are talking about?
Okay. Okay. Let's say this is my X, random variable is X. And we are taking a simple one coin
Yeah.
toss experiment, okay?
Right.
This is fx of X, or I think you have denoted as px of X, right? So this is head, this is tail. So head, if I'm considering head as success, so probability of H would be P, right? So it will go on till P. This is P. And T is 1 minus P. So let's say it can be anything. So if I mean, we can write this as 1 minus P.
Okay.
Or wait, or maybe if we let's say we restrict, let's say this is my 1. So 1 minus P would be this,
Yeah,
no?
somewhere close to the p.
Or okay, instead of that, instead of P, let's take a number. Let's say P is 1/2. So 1 minus P is, or okay, let's take P to be 1/4 and 1 minus P to be 3/4. Okay.
Yeah.
That's better. So we are saying probability of head is 1/4. So let's say this is my 1. So this will be my 1/4. This is 1/4. And 1 minus p is 3 by 4. 3 by 4 would be somewhere here. So this is what it will look like. This is 3 by 4.
Okay.
Yeah.
Okay.
Okay. Also, we can also write down the expectation and variance. So I'll just write down what is expectation for.
But then why do we call that as Bernoulli distribution, ma'am? Because generally distribution means like probability of various events and what their respective, events and their respective probabilities. When you add them up, you'll get one and all that stuff, something like that, right, ma'am? Area under the curve, something like that.
Okay.
For example, normal distribution, the
This is
area under the curve is one, we say, right, ma'am?
area under the curve is 1, but this is not a continuous distribution, right? This is a discrete distribution.
Oh, okay, okay.
Yeah, so the probability should add up to 1. And you can see you have only 2 outcomes, a success or a failure,
Correct.
right? So the total probability should add up to 1. Probability of success plus probability of failure should add up to 1.
Yeah. Actually, yeah. Fine, ma'am. Understood. Got a bit confused with the continuous distribution.
Yeah. And so I will also write down what is expectation and variance. So if we are saying X is Bernoulli distributed with parameter P, then expected value of X is given by P and variance of X is given by P times 1 minus P. Okay, you should remember this. It is very important. You'll come across many questions where you could see, okay, this is a Bernoulli setting, and when they ask you to find mean or variance, you should be able to write it directly.
How do you read this, ma'am? X.
Expected value of X is P and variance of X is P times 1 minus P. You can look at the proof I think ma'am has done in the lecture. I am just writing down what is expectation variance here.
Yes, ma'am.
Yeah. Okay. Now coming to the binomial distribution. In case of binomial distribution, you have the setting like you have x1, x2, xn. Like each of them are independent. And each of these x's are in itself a Bernoulli P distribution. And let's take and P and N is let me see what ma'am has used a notation. Okay, the same notation, right? Okay. So, all right. Here, N, what does N denotes? N denotes number of trials. And P denotes probability of success. Okay. Now, this x1 if all these xi's are independent, like x1, x2 up to xn, if they all are independent and they all follow the Bernoulli P distribution, right? Then we say that x1 plus x2 plus up to xn is a binomial distribution with the parameter n comma p. Okay. So like Bernoulli has only one parameter, which was p, but binomial has two parameters, which is n comma p. Okay. So this sum of all these random variable, we call it, this forms a binomial distribution. Okay. And what does it gives? It gives the total number of successes. So this models the total number of successes in n independent trials. Okay. So you can easily see that this is what it should give. It should give you the total number of successes in n trials, because see, x1 is taking the value 0, 1. I mean, either x1 is a success or a failure. Again, either x2 is a success or a failure, x3 is a success or a failure, so on till xn is a success or a failure. This is how it will go. Now, if you add everything, if you add x1 plus x2 plus x3 till up to xn, then this will give you all the successes that you got in n of these trials, right? And this is what exactly the binomial random variable models. So x1 plus x2 plus up to xn, this is nothing but a binomial random variable with the parameters n comma p. For example, toss 2 coins independently. Define, okay. Can you tell me, okay, define success as getting ahead. This is a success. Now, if you toss these 2 coins independently, then the question is, what is the probability that you will get 0 heads? So when you define the success as getting ahead, right? So, and the question is, what is the probability that you get 0 heads, right? So when you toss 2 heads, so basically in the question, we are interested in knowing that how many heads you will get when you toss the coins 2 times, right? So x is defined as, this random variable x is defined as number of heads in 2 tosses. And what all values x can take? So,
0,
yeah, so
1,
basically range of x.
0 to
So
X take 0 to
1,
4.
2. How it
2.
can be 4? It can only go to 2. Right?
Yes.
So range of a binomial random variable, I'll mention it here. So range of, so if I denote this as x, so range of x will always go from 0, 1, 2 up to n. Okay. So in this case, n is 2. So range is 0, 1, 2. Right. So where each of these x's, like for example, head in the first, number of head. If you get head in the first toss, if you get in the second toss, each of them independently are Bernoulli random variable, right? Now you have to find what is the probability that x equal 0. What is the probability that you get 0 heads?
1/4.
1/4.
Yes, ma'am.
This is easy, but there is like for example like this, which is very simple. It's better to just calculate it, but many a times you would come across questions where giving the answer is not very straightforward. Okay, so you have whenever
Ma'am, your voice is breaking.
my voice
No,
is
ma'am.
big, no.
No, ma'am.
No, I'm able to hear.
Okay, so whenever you come across any question where you see the setting is something like a binomial distribution, then in that case, the PMF for binomial distribution is given as, so Px of x is, and this I can write it as probability x equal x. Okay, probability x equal x equal n choose x, p to the power x, 1 minus p to the power n minus x.
N minus x.
Okay, so you can always use this formula where x is, this small x is what? This small x is whatever the value x is taking. So in this
Yes,
case, x was taking the value 0. So you put
0.
x to be 0, and what answer will you get? You will get n choose, and n was 2. So 2 choose 0, 1/2 to the power 0, 1/2 to the power 2, which is 2 choose 0 is 1, and 1/2 to the power
1/4.
is 1/4.
Ma'am, n is 2 or 3, 3, ma'am?
N is 2, no? N is number of trials. Here you are tossing the
Oh,
coin 2 times. So number of
okay.
trials is 2.
Okay. And
Okay.
0 is the
0 is what you are interested. You're interested in getting 0
0.
heads.
Okay.
So 0 heads means, and I have defined my random variable is number of heads in 2 tosses. So number of heads can be either 0 or 1 or 2. And now what I want in the question is, like, what is the probability that you get 0 heads? So I'm interested in probability x equal to 0.
So, ma'am, what is P here? Is P the same as P of x equal to 0, or is it different?
P is probability of success. P is probability of success. Here we had looked at, right? P is probability of success. So
Yes,
each
ma'am.
of these random variables, x1, x2, up to xn, they all are Bernoulli P distribution, where P is probability of success.
So, ma'am, can we get P by putting any value of x? Means x is equal to where it is x given.
What? Can you repeat?
Capital X equal to small x. So we can get any value of small x.
So small x would belong to the range of x. Range of capital X.
It will be mentioned in question.
No, it is random variable. Small x, it is 0, 1, and 2.
But in this question, we can take only 0, 1, and 2.
Yes. In this question, it can only be 0, 1, 2.
Yes.
Ma'am,
We can't take any value.
Yes.
Number total number of outcomes in this case is just 4.
Total number of
outcomes, like if we toss 2 points, then we get 4
your voice is breaking. I couldn't hear.
Ma'am, if we toss 2 coins, then we get 4 outcomes.
If we toss 2 coins, then you have 4 outcomes. That is true.
Then by taking 2,
Okay, so no, that is fine. I mean, when you're tossing a coin 2 times, it is true that you will get the outcome as HH, HT, TH, TT. Now, what is the question? The question is, what is the probability that you will get 0 heads? So 0 heads means only TT you will have, and this probability is just 1/4. So instead of solving like this, what I told you, solve it. You see this problem also as a binomial distribution, right? So where we are taking each of these x1, I mean, each of these x1 and x2 as individual, like x1 is outcome of the first coin, x2 is outcome of the second coin, right? Sorry, not outcome. X1 is number of heads on the first coin, x2 is number of heads on the second coin, right? So see it as a binomial setting where each of these x1, x2 are Bernoulli 1/2 distribution. Then if you do x1 plus x2, that will give you the total number of heads that you will have when you toss the coin 2 times.
Ma'am, so we don't have to look the number of the sample outcomes in the sample spaces. We have to just look at the how many times that Bernoulli trial has occurred, no?
Yeah, that is, I mean, that is another way to look at it, I'm saying. I mean, of like, if you look at this question, going through this is much easier, right? But just to give you an idea of like how do you approach any problem, any problem that has a binomial distribution.
Yes, ma'am.
So,
Ma'am, like here we will take the n as 2 because we don't have to count that sample space outcomes now. And so n will be 2.
Yes.
Here we can find also expectation.
Yes, we can also find expectation.
N into P.
Yeah. So expectation, see, I will tell you. So you saw that when x is, how to remember this? So when x was Bernoulli P, we saw expected value of x is P and variance of x is P times 1 minus P. Now we are saying x is a binomial distribution with the parameters n comma P, and this x is nothing but sum of the Bernoulli, so x1 plus x2 plus up to xn. So when you find expected value of x, this is nothing but expected value of x1 plus x2 plus xn by n. And this is the sum of, or maybe you would not have seen this. Okay, let's not do this. I think you would not have seen this. So okay, I can just write what is the formula for expected value of x and the variance of x in case of binomial random variable. So expected value of x is just n times p, and variance of x is just n times p times 1 minus p. So whatever you write in case of Bernoulli, just multiply by n, and that will give you binomial. I mean, the expectation and variance for a binomial distribution. Okay.
Ma'am, in binomial, like we always take the Bernoulli trials, Bernoulli distribution.
In binomial, what?
In binomial distribution, we always consider 2 outcomes like success and failure, as we did for the Bernoulli.
No, I mean, binomial is sum of Bernoulli.
Yes, ma'am.
Yeah. Okay. All right. Before we move forward to another any other distribution, let's solve the problems first. So I will, yeah.
Sorry to interrupt you. This Bernoulli and binomial, what is the difference between, means how we can, if they have not mentioned in the question, how we can
Identify.
Yeah.
So Bernoulli is like only okay. Whenever you perform only one trial, Okay. That case, it's like whenever you have only one trial, it's Bernoulli. Otherwise, I mean, when you do repetitive and independent n Bernoulli trials,
Okay.
then they becomes independent. Okay. I will take the problems now. I see problems from 11.2 and 11.3. I will take question from here and then we'll move forward. So the first question is from AQ 11.2, right? Okay. Question number 1.123. Okay. 11.2, question number 1. So I see that the question number 1, 2, 3 are all related. So we can take that. So question says X is a binomial distribution with the parameter n comma p, and x the CDF of x. So f of x is given as 0 if x is less than 0. It is given at 1024 by 3125 for x lying between 0 to 1. 2304 by 3125 for x lying between 1 to 2. 2944 by 3125 for x lying between 2 to 3. And quite big numbers. Okay, 3104, 3124. This is 3125. This is 3125. 3x4 and x. This is 4 is 5, 1 for x greater than equal to 5. This is how the CDF looks like, right? So you need to find out what is the value of n, what is the value of p, and what is the value of q. So we have not mentioned what is q. So q is nothing but 1 minus p. So q is nothing but 1 minus p. This is what we are mentioning. So how will you find number of trials in this case? Anyone? What can you do? You are given the CDF.
Yes, ma'am. Ma'am,
Yes.
first we subtract and find PMS.
Okay.
Like
So okay.
2000,
So
2300.
like, okay. So CDF figure is like x fx, and fx will always lie between 0 to 1, and x less than 0, we have 0. Now x equal to 0, we have 1024 to 3125. So let's say this number is here. Assume, let's say this is here. So this is 1024 by 3125. I will not try 3125, okay? It's just complicated. So I'll just write the numerator. I'm just avoiding the denominator term. So 1024, this is the probability that x equal to 0. So between x from 0 to 1, you have 1024. And you see 1, it's not inclusive. So I will just make a round. Okay. Now, at x equal 1, between x equal 1 to 2, you have probability, I mean, the CDF is 2304 3125. So let's say 2304 is somewhere here. 2304 somewhere here. And basically this is not 23014. I'm just removing 3125, the denominator term. So let's say this point is 2304 divided by 3125. So between 1 to 2, we are saying my CDF f of x is like this, and 2 is again not included. Now between 2 to 3, then 3 to 4, then 4 to 5. So between 2 to 3, you have 2944. So let's say this is my 2944. This is how it looks like. 3 to 4, let's say, is this. And 4 to 5, you have this. And x greater than equal to 5, you have 1. So whenever x is greater than equal to 5, it just approaches to infinity. So this is my 1. Right? So this 2304, this is 2944. Then you have 3104, you have 3104, then you have 3124. So this is 3124. Okay. So this is how the CDF is looking like. So now if you have to find the PMF, so from here, you can easily tell how many trials you have, number of trials that you have.
Yes,
X
ma'am.
is, yeah,
5.
5, right? N is 5. You can easily say X is
5.
taking the value. X belongs to
0, 1.
1, 2, 3, 4, 5. So number of samples N equal 5. Now we need to find what is P and what is Q. So how do we do that, right?
We can do one thing.
Hmm.
At x equal to 0, it will be 5c0 p to the power 0 into q to the power 5.
If C0, P to the power 0, P is 1024 divided by 3125, right? 5C0, P to the power
No,
0.
ma'am. No,
No,
ma'am.
ma'am. P we
Ma'am,
don't
it's
know.
not P.
What?
We don't know P.
Ma'am, it's not P.
P x equal to 0 we have given.
Sorry.
Ma'am,
Yeah. That's true. That is probability x equal to 0, right? Yeah, that's true.
Yes.
So 5C0, P to the power 0, 1 minus, or I will write Q, okay?
Yes, ma'am.
Q to the power 5.
Yes, ma'am.
This is given as 1024 divided by 3125. Fine.
Yes, ma'am.
Now 5 to 0 is 1, P to the power 0, 1. And so Q to the power 5 is 1024 by 3125. You will have to find So Q is nothing but 1024 divided by 3125 to the power of 1 by 5.
Yes.
Right.
And it's
4 by 5. 4
This
by
is
5.
4 by 5.
yes.
This is 4 by 5. So we found Q. Since we found Q, what is going to be P?
1 minus
Minus Q?
Ma'am, 5C5.
No,
No,
P
you
is
don't
just,
have to do this.
you don't have to do it. P is just 1 minus Q,
Okay. Yes.
right? So 1 minus 4 by 5, this will give you 1 by 5. So we found the answer as, so for question number 1, n equal 5. Question number 2, P equal 1 by 5. Question number 3, Q equal 4 by 5. Is it all right?
Ma'am, how can we say like n is equal to 5 to see after seeing the variable or random variable? 0, 1, 2, 3, 4, 5 is a random variable.
No, 0, 1, 2, 3, 4, 5 are the values that your random variable is taking. It's
Yes.
given that x is binomial NP. And the values that x is taking is 0, 1, 2, 3, 4, and 5.
Then it how to determine as the number of trials. In previous case, we see that number of trials are 2 and the x is 3, like 0, 1, and 2. In previous case.
In this case also, it's the same, no? In this case also, your x is, I mean, x, the small x or range of x
Is same.
is 0, 1, 2, 3, 4, 5. But number of trials, n, which is number of trials, is 5. Because range go from 0 to n, right?
Yes.
Range go from 0 to n, and n is number of trials, which is 5.
Okay, I
Yeah.
understand that point too.
Okay. Okay, I see one more question. Question number 5. So question number 5. Okay, let me see. Question number 5 says, for 4 independent Bernoulli trials, if P and Q represent the probability of success and failure respectively for each trial, find P probability of SSFS. Okay. Question number 5. You have to find the probability of SSFS. And what is given in the question is, you have 4 independent Bernoulli trials. You have taken 4 independent Bernoulli trials. So, I mean, from the first trial, you're getting a success. From the second trial, you're getting a success. From the third trial, you're getting a failure. And from the fourth trial, you're getting a success, right? So what is this going to be? Probability of success is what? It is given as P. What is probability of failure?
It is 1 minus P.
Q.
4 by 5.
Q. I can write Q. So again, you have success, so P. Then you
Yes.
have failure, which is Q. And then you have success, which is P. So this
Yes.
is nothing but P cube times Q. Okay.
Okay.
Ma'am.
Hmm?
Ma'am, we are not using 4C3 because the positions for the success and the failure are fixed, like it's given. That's why, na, ma'am.
Yeah, exactly.
Okay, ma'am.
Okay. Okay, now let's move to activity 11.3. So from activity 11.3, it is question number 5. Okay. Question says, suppose that 4.5% of people living in a particular city own a Creta. Okay. So 4.5% of people own Creta. A survey has been conducted to know what brand of cars people use in the city. Now, what is the probability that 12th person being interviewed is the second one to own a Creta? This is what you have to find. So a survey is conducted, and in this survey, we want to know what proportion of people or what brand of cars people use in the city. Okay. So you are interviewing people to know like what brand people have been using. Now, let's say the 12th person you have interviewed. So you have interviewed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So the question is, the 12th person that you interviewed, so this is 12th person, is the second one to own a Creta. So you have, let's say, if I define my success as owning a Creta, and see all of these, like, let's say you take the one person, you say X1 is, X1 will give you whether the person has owns Creta or not. Okay. Then you interviewed second person. Again, the second person will tell you whether that person owns a Creta or not. And so on, you will keep on going, right? So each of these Xi's is nothing but a Bernoulli P. Is nothing but a Bernoulli distribution, and P is probability of success, which is 4.5%, which is
Yes, ma'am.
0.045. Right? And so each of this person you are interviewing independently. So each of these Xi's are independent. Each of these Xi's are a Bernoulli distribution with probability of success 0.045, right? So what we are saying is at 12th place, so this is 3, 6, 9, 12. So at the 12th place, the 12th person you interviewed, so X12, what we are saying is this is my success. Okay. Let's say the 12th place, and here I have obtained a success, and this is the second success. So what we are saying is, if on 12th place you are seeing the second success, it means that on the first 11 you would have seen one success, right?
Yes.
Right. So okay, so now if on the 11th, on the first 11, if you're seeing one success, it means probability, you are interested in finding probability X equal to 1.
Yes.
The first 11.
Yes.
And what this is? This is n choose 0. So n is 11. N choose 1. P to the power 1. P is 0.045. 1 minus 0.045 to the power 10. Right?
Yes.
Can you calculate this and tell me what number this is? So I will also try. So 1 minus 0.045 to the power 10 times 0.045 into 11. So I'm getting 0.312. Okay. So what we are saying that in the first 11, probability that one person owns a Creta is 0.312. So
Yes.
overall probability that the second person, the 12th person being interviewed is the second one to own a Creta. So basically, let me write, required probability is 0.312 times probability of success, because at the 12th position, your success is fixed. And probability of that success is 0.045. So this is just multiply by 0.045. So this will give you the required answer. So
Excuse
it's
ma'am.
coming at 0.014. Yeah.
Ma'am, I didn't get the solution, ma'am. How did you approach it? Like why px is equal to 1?
Why px equal 1? Okay. So yeah, this is the right answer. Just this is the answer. Let me go through it again. The question was, let's say you are the interviewer and you want to know, like in your city, what brand of car people are using. Okay. And you have defined success as owning a car Creta, a brand name Creta. Okay. So let's say the first person you interview, either they will say they own a Creta or they do not own a Creta. Okay. Let's say the second person will say yes or no. I mean, owning a Creta or not own a Creta. Similarly, third person, yes, no. Fourth person, yes, no. And so on till you will keep on going. So each person here, I mean, if you define your random variable x1, xi as a Bernoulli P distribution, right? So it's it denotes whether each xis denote a person owning a Creta or not. That is what it gives, right? And if I'm defining the success as owning a Creta, so that probability is, and that percentage of people is 4.5. So if the person is 4.5, the probability is going to be 0.045. So each of these xis are the Bernoulli distribution with probability 0.045. Okay. Now, let's say I have interviewed 12 people. So first, second, third, fourth, fifth, sixth, seventh, eighth, 9th, 10th, 11th, and this is my 12th. So we are saying 12th person being interviewed is the second one to own a Creta. It means the 12th person that you interviewed, on that person definitely owns a Creta, and that is the second person. So far, whatever people you have, I mean, from number of people from 1 to 11, the first 11 people, out of those 11 people, you have only one success. Right? Is it clear that in the first 11, you have one success?
Yes, ma'am.
Yeah. And on the 12th position, you have one success, and that is the second, overall 2 success. Right?
Yes, ma'am.
Yeah. See, why we cannot use the binomial distribution here is because, I mean, binomial distribution for 12 and n equal 12, because when you are using the binomial distribution, you are choosing n, you are doing n choose k, right? So if you do 12 choose 2, that means these two people can be at any place from 1 to 12. right? But this is not we want. We already know that that the second person, I mean, the second person is going to be on the 12th place. So that is fixed. So now we only need to look at the first 11 person who you have interviewed. So out of those 11 people, you have seen one success, but in the first 11 you don't know where that success is. You don't know whether you received the success on the first person, or for the second person, or for the third person, or for the fourth person, and so on. You don't know where is it. So here I can use my binomial distribution formula, right? Because the setting is same as Bernoulli. You have the person from x1 to x1 to x11. Each of them is a Bernoulli 0.045 distribution, and the number of and they all are independent. They are being interviewed independently. Number of trials are going to be 11 because there are 11 number of people, and probability of success is fixed as 0.045. Now you can use your binomial distribution because you are interested in what does binomial distribution model. Binomial distribution models the total number of successes in n independent trials. Okay, so in the first 11, we are in the first 11, we want one success, right? We want one success in the 11 trials. So it is modeling one success in the 11th trial. So I can write for the first 11 people, I can have 11 choose 1. So n choose p, which is n choose x, which is 11 choose 1, because we just have to select one people. We are choosing one place. P to the power x, which is 0.045 to the power 1, and q to the power n minus x, which is 1 minus 0.045 to the power 11 minus 1. Okay, so this will give you the probability. So this is giving you the probability that you received one success in the first 11 trials. Okay, but this is not the probability you were interested in. You were interested in probability that the 12th person being interviewed is the second one to own a crater. You found the probability till 11th, but on the 12th place, you definitely have a success. And right, this is what is given in the question, that the second 12th person being interviewed is the second one to own a crater. So at the 12th position, you definitely have a success. So and each of these are independent. So we can just simply multiply the probability. So from probability x equal 1, which we have found using the first 11 people, it is coming out as 0.312 times probability of success, which is for the 12th position, which is 0.045, right? Because success is just 0.045. So if I multiply these two, I get 0.014. Is it clear?
Yes, ma'am.
Okay. So this has a very special name. Such kind of distributions are called negative binomial distribution. It also has a name, so I can just write it down. It's not required to know what the PMF for this distribution looks like, but you should just get an understanding of, like, this is nothing but you can solve it using your binomial distribution. Okay, so this kind is called negative binomial. I don't think it has been covered in lecture, but this can be easily solved using a binomial random variable. It just use simple probability and binomial distribution.
Ma'am, I have one more doubt, ma'am.
Hmm?
Ma'am, why you not taken n to be 12? Like there are 12 persons now.
Yeah, that's what I had explained in the starting. Why can't we take 12? Because you are only interested at the 12th position. You already have a success, right? And that is the second success. So, I mean, when you write the Bernoulli distribution, when you write the binomial n comma p, okay, binomial n comma p. Probability is n choose x, p to the power x, 1 minus p to the power n minus x. So what does it says? It says you have n number of trials, and out of n number of trials, you are interested in x successes. X denote number of success, right?
Yes,
So
ma'am.
in this case, like, you are not interested in number of successes in 12 trials, right? Because you already know that at the 12th position you're getting a success, that is fixed. So for the first 11, you are not sure where did you receive the first success. So only for the first 11 people, you need to find the number of successes. I mean, you need to find what is the probability that you got one success in the first 11 people. It cannot be 12 people, right? You cannot write 12 choose 1, because you're only interested in the first 11. I mean, 12, you already know that there is a success. You don't know where the success is in the first 11. So that is why we are doing 11 choose 1. Okay.
Yes, ma'am. Got it.
Okay. All right. Is there any other question? Okay, I see one more question from 11.1. Okay, let me just take that and then we can move to other distributions.
Ma'am,
Hmm.
if instead of second trial,
Hmm.
if there will be a third outcome, then we will choose 11C2
Yes.
and multiply like that.
Yes. Okay. This is from AQ 11.1. Question number 5. So you are given the PMF for a random variable x. So probability x equal x is 0.1, 0.2, 0.2, 0.3, 0.2. For x equal 1, for x equal 2, for x equal 3, for x equal 4, for x equal 5, right? Now define a Bernoulli random variable y. So define, or let's write it here. Define y as y equal 1 when x is less than equal to a, and 0 for x is greater than a. Okay. Where a belongs to the positive integer. For what value of a Bernoulli trial of y be considered as the most uncertain Bernoulli trial? For what value of a Bernoulli trial of y be considered as the most uncertain Bernoulli trial? X is taking the values 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So a can be any of these numbers, either 1 or 2 or 3 or 4 or 5. Now if x is less than equal to a, so let's say if I take, for example, if we take a to be 1. Then we are defining y to be 1 if x is less than equal to 1, 0 otherwise. It means when x equal to 1, we have a success. I mean, y will have a success. So in this case, you have for x equal 1, you have y equal 1. Then if we take a to be 2, it will be x less than equal to 2, x greater than equal to 2. So if x is 1, 2, your y is 1. This is how, I mean, if x is 1, 2, 3, y is 1. X is 1, 2, 3, 4, y is 1. X is 1, 2, 3, 4, 5, y is 1. Okay. Has it been mentioned in the question what is meant by the most uncertain Bernoulli trial?
No, ma'am.
No.
No, ma'am. It's not given anything about uncertain. What is uncertain here?
Okay. It is given in lecture. Can you tell me where it is given? Okay. Yeah, I saw. It's related to variance. So the most uncertain Bernoulli trial is the one with the largest variance. Largest variance, right? Yeah. So variance of y just give me a minute. Okay. Where were we? Yeah, you need to find the variance of y, right? So variance of y is going to be p times q. So okay, if x equal 1, if x is just singleton 1, then you have something like this, right? So what is variance in this case? X equal 1 will give you success. So P is 0.1 times .9, right? And this is 0.09. Then take the second case when variance of y, when x is, when a is 2. When a is 2, you can have x taking the value 1 and 2. So in this case, probability of success, probability of 1 is, 1 is probability of success, probability of 1 plus probability of 2, which is 0.1 plus 0.2. This is 0.3. So 0.3 times 0.7, which is 0.21, right? Now, in the third case, when a equal 3, so when a equal 3, x can take the values 1, 2, 3. So probability of success would be 0.1 plus 0.2 plus 0.2, which is 0.5. So 0.5 times 0.5, which is 0.25. And in the lecture, you have seen that the most uncertain Bernoulli trial occurs at when you have the largest variance. And the largest variance for the Bernoulli random variables occurs when your probability of success is 1 by 2. So I can write my answer to be a equal, when a equal 3.
Okay, ma'am, got it.
Got it? Okay.
Yes, ma'am.
Ma'am,
Yes.
why you have taken 0.5 means 0.5 multiplied by 0.5 means every time you are taking 0.9, 0.7, 0.5. Those are the different values, right?
No, I'm not getting.
Actually, expectation means variable equal to x square minus ex whole square, right?
Here we have used p into 1 minus p.
Okay. Okay, got it.
You got it?
But still 1 minus p. Why it is changing every time? P is changing
Because
every time.
because we are taking for different cases. So your x is 1, 2, 3, 4, 5, right?
Okay.
And the way y is defined, it is y equal a success when x is less than equal to a and failure otherwise, right?
Okay.
So y is a Bernoulli random variable, and the variance of a Bernoulli random variable is p times q. Now these a's, you can see that this x is nothing but this random variable x, whose PMF is given to you. So here x is taking 5 distinct value, which is 1, 2, 3, 4, and 5. So a can take either 1 or 2 or 3 or 4 or 5. So now we are taking different cases. So let's say the first case is when x equal when A equal 1. Okay. So when A equal 1, what happens?
Sorry to interrupt you, ma'am. Bernoulli trials means what? Independent and identical. So
No,
every
Bernoulli trial is just, you have only one trial. You don't have, how do you have any independent? I mean, you're talking about only one trial. That is a Bernoulli trial. And in that trial, either you can have a success or a failure.
Okay, Bernoulli trials, not binomial. Correct?
Correct. Yeah.
Okay, okay. Got it, ma'am.
Okay. It is clear, right?
Ma'am, can you explain the graphs of binomial distribution, like when it is right skewed and left skewed? Just a little bit.
Okay, we are already at 7:35. Okay. Has the skewness been discussed in the lecture? Has the skewness been discussed in the lecture? Can you tell me?
Yes, ma'am.
What, ma'am?
No, I'm just asking if skewness has been discussed in the lecture. What is left skewed? What is right skewed?
Yes, it is already discussed. It is
Okay.
already discussed in lecture.
Okay.
Ma'am,
Hmm.
sorry to interrupt you, but the previous question, which question you was discussing? Activity?
Activity 11.1, question number 5.
Okay, thank you, ma'am.
Yeah.
Oh, ma'am, please discuss about in Poisson graph. Poisson distribution.
Yeah. Okay.
Ma'am, skewness discussed before the hypergeometric distribution.
Let me go through Poisson first and then I'll come to hypergeometric. See what all is covered. Okay, the derivation and all, we will not do it. We don't have that much time. So if you are interested, you can go through the derivations. We'll just talk about what is a Poisson distribution and what does it PMF look like. Okay.
Yes, ma'am.
Yeah. let's say X is a Poisson distribution that has parameter lambda. So we say the distribution of X, which is probability X equal X, is e to the power minus lambda, lambda to the power X by X factorial. So the question is what the lambda is here. Lambda is the rate, or this is also the average that you calculate. So like in Poisson distribution, I mean, whenever you have the situation like whenever you're interested in like in a fixed interval of time, like let's say you are starting from here and you are dividing your time in like fixed interval. Let's say you're dividing your time in fixed interval, and you want to know in each of these fixed interval how many times that number of times an event has occurred. So the situation like the number of accidents that happens on a highway every 1 hour. Okay, so let's say you're looking at every 1 hour how many accidents has happened. So that will be here. Then you will again from 1 to 2 hour you will look at how many accident has occurred, and then again from 2 hours, second hour to third hour, you look at the number of accidents. So situations like this models your Poisson random variable, and this yeah, so situation like this gives you the Poisson random variable, and its PMF is given by e to the power minus lambda, lambda to the power X by X factorial. Here what is X? X is number of times an event has occurred. We'll look at first one example and then we understand what like how does it look like. So I saw one question in the chat somebody had posted, so we'll go from there. Okay, or maybe I'll take from your activity questions. So can someone tell me if you have any doubt from Poisson distribution, like AQ 11.8, AQ 11.9?
Ma'am,
yeah.
Question number 3, 5, and 2.
2, 3, and 5. AQ 11.8, question number 2, question number 3, question number 5. Any other question from AQ 11.9 or 11.8?
11.9, question number 2, 3, and 4, 5.
2, 3, 4, 5.
Yes. I have calculated, ma'am, but I'm getting wrong answers.
Okay. Let's discuss this question, okay? Maybe I'll do not this many number of questions. I will do 1 or 2 problems, rest you can do it yourself.
Okay, ma'am.
Yeah. We don't have much time. Yeah. Let's look at AQ 11.8, question number 2. It says X denote the number of radioactive particles. So number of radioactive particles passing through a counter in 1 millisecond time interval. Passing through a counter something in 1 millisecond time interval. So we are considering the interval as 1 millisecond. Okay. Probability that number of particles passing will not be counted is 0.01. Not counted. Assuming that X follows a Poisson distribution with the parameter lambda equals 3, then find the probability that the number of particles counted during a specific time interval is 3. So in any particular time interval, probability that your number of particles counted is 3. So you know that probability, if X follows a Poisson random variable with the parameter lambda, then probability X equal X is e to the power minus lambda to the power X by X factorial, right? So probability X equal to 3 would be what? E to the power minus 3 to the power
3.
3 to the power 3 divided by 3
3 factor.
factorial, right? Wait, I think there's some. Let X denote the number of radioactive particles passing through a counter in 1 millisecond time interval. We are considering the time interval of 1 second each. Okay. Probability that number of particles passing will not be counted is 0.01. Assuming that X follows a Poisson distribution with parameter lambda equal 3, find the probability that number of particles counted during a specific time interval is 3. X is Poisson 3. This is not coming as the answer, right? I'm not sure why this is not coming. Let's look at the second problem and maybe figure out what the error we're making. Question number 3, it says number of items sold by an online store in an hour follows a Poisson distribution. So let X denote number of items sold in 1 hour. And we are saying X follows a Poisson distribution with parameter lambda equal to. So the rate is like every 1 hour, I mean, you're selling 2 products. So find the probability that in the next 4 hours, exactly 3 items will be sold. Probability X equal 3. So in you have e to the power minus lambda to the power X by X factorial. Okay. So in 1 hour, number of items sold is 2. So in 4 hours, you will have 8.
Okay.
Let's see. Okay. Yeah, this is fine. E to the power 3 by 3 factorial, and we are getting this as 0.028. This is right. So I don't know why we got wrong for the first question. Is this clear to you? Why we did
Yes,
8?
ma'am. Yes, ma'am.
Why we
Got
did 8 is clear to you?
Yes.
Let me see. I'm not sure why what is wrong in the first one. So in first one, my parameter was, we were looking at 1 millisecond time interval. Probability. Okay, I'm not sure about the second question. Okay. This is fine. Let's look at one more question and then we can move to other distribution. Also, when X is a Poisson lambda distribution, your expected value of X equal variance of X equal lambda. Okay. Let's look at AQ 11.9. Question number 2. A manufacturing company produces medicine bottles. It finds that probability of producing 3 defective machine bottles is 2 by 3. 3 defective bottles is 2 by 3 times the probability of producing 4 defective medicine bottles. 4 defective bottles. Assuming that the number of defective medicine bottles in the company follows the Poisson distribution. Based on this information, answer the question 2 and 3. Okay, you have to find the average number of defective medicine bottles. So average number of defective medicine bottles means you need to find what lambda is. Okay, you don't know that. So 3 defective bottles means what? This should be e to the power minus lambda, lambda to the power 3 by 3 factorial. This is 2 by 3 times e to the power minus lambda, lambda to the power 4 by 4 factorial. Right? This gets cancelled out. This gets cancelled out. And you're left with lambda equal 4 factorial by 3 factorial times 3 by 2.
Why, ma'am, 3 by 2?
You have lambda here, right?
Okay,
4.
here. Yeah, got it, got it.
So this is 4 times 3 by 2. This is just 6. So lambda is 6. So this is the average number of bottles, average number of defective bottles that the company is producing. Is that okay?
Yes, ma'am.
Okay. That was about the Poisson distribution. We are left with one more distribution, that is hypergeometric. So in the hypergeometric, this is again like this looks like something like this. Suppose you have a population and you are dividing your population in like either a success or a failure. Let's say this population size is n, and or instead of saying success failure, let's say type 1, and let's say type 2. Okay, so let's say type 1 object is of R type, and type 2 would be n minus R. Now what you're saying is, let's say I take a sample of size small n from this capital N, and I want to know what is the probability that you have, let's say, k objects from type 1. Okay, and this is done without replacement. I mean, you are taking let's say you are taking one sample, then you're not putting it back, and I mean you're taking one sample, then taking another sample, and so on. You're not doing like you're taking one sample, then putting it back, then again taking back, then again taking one. It's not like that. This is without replacement. Now, when you want to know what is the probability that in this n sample that you have obtained, what is the probability that there are exactly k objects coming from type 1? Okay, so this probability is given by, so k type of objects should come from type 1. So in type 1, you had total of R objects. So from there, you will choose k objects. Out of R, you choose k, and the remaining n minus k. So since your sample is of size n, so and if k objects are coming from type 1, it means that n minus k objects should come from type 2, right? So remaining n minus k objects, so n minus k objects, you will take from this n minus R objects. And since you have to choose a sample of size n, you will do n choose n. So this is the probability that x equal k. Is this okay?
Yes, ma'am.
Okay. Can you tell me any question that you face difficulty from 11.6, 11.7? Maybe I can take those questions. AQ 11.6, AQ 11.7. If you have already given, maybe you can do that. Let me see. AQ 11.5, AQ 11.6. What is 11.5?
Binomial.
Binomial distribution, is it? Binomial, let's not do any more binomial. We have spent a lot of time there. Let's take from 11.6 and 11.7. So 11.6, I see one question, which is question number 5. Say, suppose we draw 8 cards from a pack of 52 cards without replacement. What is the probability of getting less than 3 spade cards? So AQ 11.6, question number 5. So you are saying from a pack of 52 cards. So you have 52 cards. You are taking a sample of 8 cards. Okay. And the question is, what is the probability of getting less than 3 spade? What is the probability of getting less than 3 spades, right? So looking at the question, which is asking you to find the probability of getting less than 3 spades, it means your success is spade. You want to get spade. So again, you can divide your population in 2 parts. One is spade, another is non-spade. How many spade cards do you have? 13? You have 13 spade card, right? Yes, no? You have 13 spade cards? How many non-spade cards do you have? 52 minus 30?
39.
39. So what you want is probability of getting less than 3 spades. It means you want probability that X is, if we define your random variable, X as
0, 1, 2.
Number of spades. So X will take the value
0,
0,
1,
1,
2.
2, right? Because we are interested in less than 3 spade. So probability of X is probability of X equal 0 plus probability of X equal 1 plus probability of X equal 2. Okay. What is probability X equal 0? Probability X equal 0 means you are getting 0 spade. If you are getting 0 spade, it means all the 8 cards that you are getting, it's non-spade. So 39. So 39 choose 8 divided by 52 choose 8 plus probability X equal 1. It means you have 1 spade card and remaining 7 cards are coming from non-spade. So from spade, you choose 1, 13 choose 1. From non-spade, which is 39, you choose 7 cards divided by 52, choose 8. Then probability x equal to means you are choosing 2 cards from spade and 6 cards from non-spade. So 13 choose 2 times 39 choose 6 divided by 52 choose 8, right? And this will give you, just solve this and you should get an answer. So 1 by 52 choose 8, you can take common and just multiply all this and then add.
Okay, ma'am.
Any other doubt in any question? So if you have no doubt, should we close?
Yes, sir. Thank you, ma'am.
Yeah.
Yes, ma'am.
Thank you. Thank you all.
Thank you.